Video number 3 is on section 4.3, using angle bisectors. So, last video, we talked about, actually no, back up even more. The very first video that we had, we talked about what it could possibly mean to be the center of a triangle. And I proposed 4 different ideas, or I said that there would be 4 different triangle center points to talk about. One of them was the circumcenter, and that was last video. That was where the perpendicular bisectors met each other. So this one's going to be very predictable in that we're going to have some type of segment that relates to a triangle somehow, and we're going to talk about how that yields bigger things, including a point that we could conceivably call the center of a triangle in one regard or another. So, to talk about angle bisectors, which are way more obvious than perpendicular bisector. A perpendicular bisector, again, cuts a segment in half, basically. An angle bisector is going to cut, as the name would suggest, an angle in half. So it'll cut one angle into 2 smaller congruent ones. Keep that in mind when we talk about the next thing, which, here's a blast from the past. If I want to think about the shortest distance between 2 points or lines, or a point and a line, I should say, if I were to draw a point and say, find the shortest distance that point is from that line, you wouldn't tell me this, probably. Number 1, because it's crooked. Number 2, because I could think of a shorter distance, which would be a perpendicular segment. Let's keep that in mind, because it's going to be relevant when we move on to the next point, which is going to be talking about the angle bisector theorem. So, if a point is on an angle bisector, an angle's bisector, then it is equidistant from the angle's sides. And when I say the sides, I mean the 2 sides that would make up that angle. And then I ask why, of course, because I always do. So, the implication here is that since D is on the bisector of angle A, or BAC rather, then that's going to imply that BD is congruent to BC. So as far as showing that that's why. Oh, I never finished the T in segments up here. Whoops. Rookie mistake. Clearly my first year with these videos. So, let's actually show this. Our goal here is to show that BD is congruent to DC. Or in other words, these 2 blue segments are congruent to each other. So how can we do this? Something familiar should stick out to us, which is that I see 2 triangles. If I could show those 2 triangles congruent to each other somehow, then I could use CPCTC to show that the blue segments are congruent as well. So, I'm given that BAD is congruent to DAC, because of the angle bisector, definition of. I have that angle B and angle C are right angles, cool, that's an A for us, and I have that AD is congruent to itself. So it sure does look like I have AAS triangle congruence, followed up by CPCTC. Cakewalk. That would give me, because this top triangle and this bottom triangle are congruent to each other, that would give me that BD is congruent to DC, which implies, based on the definition of congruence, that D is an equal distance from B and C. Cool. So if I now look at the converse of the angle bisector theorem, again, we're going to look at the if-then statement that is the original, and then flip the 2 parts. So, how do I flip the following? If a point is on an angle's bisector, then it is equidistant from the angle sides. This is, oh boy, this is exactly like what we had last class. Oh my gosh, class. Exactly like what we had last video. Deja vu. Let's just flip the if-then parts. If a point is equidistant now, also notice how my handwriting is improving, equidistant from angles sides, then it is on its angle bisector. Keep this theorem and this converse theorem in mind as we move on to the next page. And actually we do some stuff, some mathy stuff. So, try to find the indicated measure. If possible, state which theorem was used. If not possible, state what information is necessary further. So for this first example down here, which I will do in purple, I want to find the measure of GFJ. GFJ is this guy. And, boy, if it's anything at all that we know, it is certainly 42 degrees. But do we know that? Can we use some kind of theorem to back that up? Well, J is equidistant from G and H. That means that it's on the angle bisector. So that means that JF happens to be an angle bisector. And since it's bisecting GFH, oh my gosh, what a mess, that means that this angle, JFH, and this angle, GFJ, the one we're trying to find, are congruent. So I guess that makes her 42 degrees. Awesome. So let's see if we can do the same thing over here for example number 2, which I'm going to do in, what color should I do it? Blue. Why not? Find x. Okay, so if anything, x is going to be 15, but let's see if we can actually deduce that. So, in order for that to be the case, whatever this point is, if it's going to be equidistant from both of these sides, or in other words, if x is 15, then we have to know that this ray is an angle bisector. So we need to ask ourselves, do we actually know this? And it doesn't look like it. It really doesn't look like it. We know this guy is 27, but we don't know anything about the angle above it. So we certainly don't know if it's also 27, which means we don't know if this ray is an angle bisector. Which means we don't know, notice how we're going all the way backwards here with our logic. So we don't know if this point that I'm bolding is on the angle bisector, which means we don't know if it's equidistant from the sides. So who knows what x is here? Not us. So what information is further necessary? We would need to know, we must know that this is also 27 degrees. That would tell us that our point is on the angle bisector, which would be sufficient to show that x is also 15. So as far as this thing on the right goes, example number 3 here. Let's choose green. Well, we're told the ray is an angle bisector, rather. Good. Which means that since this intersection point right here is actually on the angle bisector, we can show that these two segments are congruent. This point is going to be equidistant from the sides of the angle, so we know that this point is going to tell us these two blue segments are congruent to each other. Cool. So I guess 5x equals 6x minus 5. A little bit of easy math gives me 5 equals x. Neat. Oh, and also I forgot this. Shame on me. There's a gnome here. Ha ha ha, got you. Let's go to page 3. Okay. The incenter of a triangle. It is the concurrency of, ready for this if you couldn't figure it out, it is the concurrency of the angle, that was bad, angle bisectors. That's what we're talking about this section, so that shouldn't be a surprise to us. It is equidistant from each side of the triangle. So, if I look down here, I learned my lesson from last time. C is the center, or it's the incenter of this triangle, or so we're imagining. Or so we can actually see, because, look, we can see that IC and CN and EC are all angle bisectors, which means that since this is the point of their concurrency, that's going to be the incenter. This tells me that C is equidistant from the sides. How do I show this? Well, I could draw a line to the sides, and that would tell me that these are the shortest distance to the sides. Since they are the shortest distance, this would imply that they are perpendicular to it, but have some kind of diagram that looks like this. What a mess. But if I know that this is the circumcenter of, this is the incenter of a triangle, these distances are going to be congruent, the distances are going to be equal to each other. So one way to look at this is, I could think of each of these points as being on a circle, each of these points where it intersects the side of the triangle. If I were to try to draw it, you know what, not bad. That circle right there has the same radius, which is the distance from each of these points on the triangle to the actual incenter, C. And that's called an inscribed circle. A circle is inscribed inside of this triangle. The circle touching each, an inscribed circle is described or defined as a circle touching each side of a triangle. Fine. Thus the triangle is rounded. That's kind of how it's different from a circumscribed circle. In this case, for an inscribed circle, the inscribed circle is inside of the triangle. The circumscribed circle is outside of it. As far as where it's located. Alright, here's where I have to bust out of this again to just point my iPad at the screen of my laptop. Here we are. This is another GSP file that you have access to called 5.3incenter.gsp. So, this is a lot less interesting than the last one because, as it turns out, if I move stuff around, it gives me something not that interesting. I don't have any points labeled, I don't have anything labeled really, but I could already notice that the red segments are the angle bisectors. Look, I can see this angle here is congruent to the one below it. Red line going through would have to be an angle bisector. My voice cracked there, I don't know if you caught that. And their point of concurrency, the point where they all meet, is this guy in the middle, meaning that that is the incenter, which also makes sense because it is equidistant to each of these sides. We know that because, well, each of these distances would have to be the radius of the circle. Fine. So as far as its location, we talked about this last time in regards to the circumcenter, and sometimes how the circumcenter is inside of the triangle, sometimes it's outside. No matter how I fiddle with this thing, the inscribed circle and the incenter is always going to be inside of it. Always going to be inside of the triangle. So just to go back to take this note down, it is always located inside. Also, if you haven't found the gnome on this page, here he is in the top left. So to do some actual math, here's a diagram that looks a little bit familiar to us, because it kind of looks like the same one that went with the circumcenter, except all our ingredients this time are different. We don't have a circumcenter. We don't have perpendicular bisectors. We're told, in this case, that n is the incenter. We're told that the blue segments are perpendicular segments to the triangle sides, and we're told that the red segments, most importantly, are angle bisectors. Fine. It makes sense because they are all concurrent with n. Therefore, that's proof that n is the incenter. And the blue segments that are perpendicular to the sides, okay. Well, since we know n is the incenter, we know that it's equidistant to the sides. So since these blue segments are perpendicular to the sides, that would imply that these are the shortest distances. So this guy is the shortest distance from n to AB. So what this tells me, or what I can conclude from the fact that n is the incenter, is one of the facts that we already know. So NF, NE, and ND are all congruent to each other. And if I were to draw the inscribed circle, which I'm going to do poorly, yeah, there it would be, where EN and NF and ND are all radii of that circle. That was an embarrassing drawing, so I'm just going to get rid of it again. Okay, so let's keep all this stuff in mind when we actually answer the questions here. Find NF. Find NF. Okay. This looks hard. But if I go about this in such a way, well, my first reaction was to say, can I find the length of any of the other blue sides because they're congruent? The answer is no. I don't see any ways. This 20 goes with AN. The 35 on the bottom goes with CD, and none of those seem to do anything for me until I try to pick apart what I'm looking at here and specify in this diagram what's necessary to get what I want. Whoops. And I can see that in this green triangle I make, it's a right triangle. If this angle below it right here is 90, then the one inside of the triangle is as well. Cool, which means again I could use the Pythagorean theorem. Maybe we could do this one in our head even, but I have x squared plus 16 squared equals, am I going to run out of room? 20 squared. Yes, I am almost. So that's x squared equals blah, 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 blah. So I'm going to stop right here because I already know the answer is, and I imagine you know how to do the Pythagorean theorem too. I already know the answer is 12. How do I know this? Well, we know something about special right triangles, or at least if we don't now, then we will. A 3, 4, 5 is a special type of right triangle because 3 squared plus 4 squared equals 5 squared. So as it turns out, if you start multiplying these factors, or these numbers by the same factor, like 2, 6, 8, 10, will also satisfy the Pythagorean theorem. 6, 8, 10 is a relative of the 3, 4, 5 by a factor of 2. So I happen to notice up here that x 16, 20 is a relative of the 3, 4, 5, in that it makes x, should have chosen a bigger eraser for this, it makes x be 12. 12, 16, 20 is a multiple of 4 of my 3, 4, 5 right triangle. So NF is 12. If you don't understand what I said, or if you just straight up don't like it, that's fine. You can use the Pythagorean theorem to find x anyway. NF is equal to x, which we found to be 12. Cool. dn. All right, well, dn is congruent to NF, so that was easy enough. That's 12. Now Cn. Okay, looks like we have some more silly Pythagorean theorem business going on here. And I don't know if there is a special right triangle rule we can apply here. We might just have to do this the old-fashioned way. We might just have to say 12 squared plus 35 squared equals Cn I'm calling y squared. So, I don't know if you can tell that I just paused the video, but I did, so I can use a calculator to cheat here. This is 144 plus 1225 equals y squared. The sum of those two numbers on the left is 1369, and this is already looking like it might come out to a perfect square. If I take the square root of each side, and if I ignore the negative answer, because negative lengths don't make sense in geometry, I'll get y equals. The square root of that is 37. That's right, I kind of forgot that. A 12, 35, 37 is another special right triangle, where all of the values are integers. Won't always work out that nicely, but it does now. So, Cn is equal to 37. That's about all the notes I have for you today. Make sure to try those practice problems, and we're going to end at exactly 16 minutes.